Now we're ready to look a little bit deeper into some of the applications of how we can use the central limit theorem in calculating probability. Again, in solving word problems, we always want to start out with a picture, and we would really use the same procedure as we did previously in modules 8.4 and 8.5. We always want to draw a picture and label the curve according to the parameters of the information that we're given. We're either going to use normal CDF or invert norm, depending on what we're after. Remember, normal CDF is always giving us probability and area, whereas invert norm, we are given probability and area, and we're looking for the value that is the border value along the horizontal axis. On our calculators, matching what we're entering to the graph we have created. Our standard deviation has changed now with our sampling distribution. And then we always want to make sure we actually answer the question that was posed using complete sentences and our phrases. For after the z-value, our data value, the formula changed. Sometimes calculating the z-value is helpful because it tells us how extreme or non-extreme the given individual data value is. Since we're dividing by not the standard deviation of the population, but rather the standard deviation of the sampling distribution, we have to take sigma and divide it by the square root of n. It's important that as you enter this, you put parentheses down here because as you put it into your calculator, you should have parentheses around the bottom value, and you should also have parentheses around this top difference in order to calculate the correct z-value. So let's start out with an example, and we're pulling from our information that we had on earlier for body temperatures. Body temperatures of adults are normally distributed with a mean of 98.6 and a standard deviation of 0.73 degrees Fahrenheit. What is the probability that a sample of 36 adults would have an average normal body temperature that's less than 98.3 degrees Fahrenheit? So first of all, here's a picture of our population numbers. And actually, remember that the population has a mean of 98.6. So as we picture the sampling distributions of samples of 36 adults, we can get an idea that 98.3 is going to be somewhere here on the left. To figure out really how far to the left, we would need to look at what the z-value would be. In other words, we're translating it from our original data over to what it would be on the standard normal curve. This will give me an idea of how many standard deviations I am away from the mean. As we plug our values in, notice that the mean of 98.3 is entered. We subtract the mean body temperature 98.6, and we divide by, remember to use parentheses, 0.73 over the square root of 36, and close those parentheses off. See, we're at negative 2.47. So, on the standard normal curve, we're almost 2.5 standard deviations away from the mean. So we can see how these line up. Now, for after this area, the way we find that is by taking, let's go back here. This area that we want, we would calculate the area to the left of negative 2.47. Now how we do that, we're going to look at that on the next slide. So, the mean body temperatures of adults are normally distributed with a mean of 98.6 degrees, standard deviation of 0.73. So they're the same data we were looking at before. What is the probability of a sample of 40 adults having an average normal body temperature greater than 99 degrees Fahrenheit? So here's our probability we're after. What's the probability that a sample of 40 adults would have an average that's greater than 99? So here's 99. It's kind of far away. This is the desired area I'm after. We really don't have to find the z-value that's associated with 99 in order to calculate the area. On the previous slide, we did simply to get an idea of how many standard deviations we are away from the mean, and we can always do that. But our calculators don't require us to change 99 into a z-value. Instead, if we go 99, think of this again in boundary terms, 99, and we want the area to its right, so we're going to go to something large like 1,000. We put the mean of the distribution, and then here we enter the new standard deviation. You don't even have to get the decimal, just enter in standard deviation of your population divided by the square root of 36. Here we get 0.003. This is the area to the right of 99 degrees, and hence this is my probability. The biggest thing that you have to adjust when you're working with a sample from a population is that it's slightly different than what we do with an individual data value that we select from a population. The standard deviation is changed once we pull more than one item from our population, and it changes by the square root of that sample size. So since the area to the right, 99, was 0.003, we say the probability that a randomly chosen sample will land way up here, higher than 99, is 0.0003, or 0.03%. Let's look at a contrast then for the probability of a sample of one item to a sample like what we found here, a sample of 40. So again, same parameters for our problem, but first of all, let's look at the probability of selecting one person from our population that would have a temperature less than 98.2. So here's our probability distribution, and let's figure out where approximately 98.2 would fall on my curve. It's negative 0.547. Notice that in calculating this z, I'm only taking a single person from a population, and so the denominator here is not divided by anything except for the standard deviations, 0.73, which is the standard deviation of my population. Even if we use that other formula, we would be dividing by the square root of 1, which is still 1. So we would just end up with 0.73 anyways. So in terms of distance from the mean, if we're less than half of a standard deviation from the mean, 98.2 wouldn't even make it to -1 standard deviation. The area we want then is the area less than that. So as we go to our calculators, we put in normal CDF, -1,000, 98.2, 98.6, the mean of my population, and then the standard deviation of my population, 0.73. The probability is 0.2919. In other words, there's approximately a 30% probability that a single body temperature will be less than 98.2. Here's how we write that in probability notation. The probability that x, an individual data value from my population, will be less than 98.2 is 0.2919. Now let's look at not a single person, but rather a sample of 36 people pulled from my population, and having the same body temperature average less than 98.2. Looking at the z-value, if we plug this in, and remember, instead of dividing by 0.73 now, we're dividing by 0.73 divided by the square root of 36, my sample size. What you calculate with z comes out to be -3.228. That means we're more than 3 standard deviations away from my mean, with the same body temperature. The big difference here is simply what we're dividing by. In this problem, we divided by 0.73. Over here, when I calculated the z, I divided by 0.73 over the square root of 36. This moves this value further to the left, meaning there's going to be less probability because we have less area. Normal CDF, -1,000, almost the same number. And notice the only thing we've changed here is the standard deviation, but that immensely changes my probability. I went from having a probability of 29% to having a probability of 0.05%. The main reason why this happens is that as my standard deviation decreases, we have a lot less tolerance for deviation away from the mean. So something here, which was only 4/10 away from the middle, 4/10 becomes a much larger distance because my standard deviation is much smaller. So let's work a couple more problems together. A book publisher claims that its average book size is 250 pages with a standard deviation of 70. As a reviewer, you get paid per book and not per page to read over the manuscript. What is the probability you are randomly given a book that will be less than 200 pages to proof? So here's our mean, here's our standard deviation. We know that under normal circumstances, 200 would not be that far away off from the mean. In fact, it would be less than one standard deviation. So the probability ends up being fairly high. Normal CDF, -1000 all the way up to 200, mean and standard deviation. There's about a 25% chance that I would get a book that's actually less than 200 pages to read. Now let's contrast that. What's the probability that if I took 15 books and found their average page length, that the mean page length would be less than 200 pages? As you can guess, this gives us a much lower probability. The probability that the mean would be less than 200 is 0.0028, again, 28/100% chance, which is way less than 1%. Pollster claims that the average American family spends $927 on Christmas gifts with a standard deviation of $200. What is the probability the average Christmas spending for a sample of 500 families differs from the average by less than $15? When we say differs from the average, differs can go in either direction. So if I were drawing a picture of this, I would picture the mean in the middle, and differing from that middle of 927, I would be to the left a certain distance, and I would be to the right a certain distance. So in other words, I would subtract, if we're less than 15, I'm going to be somewhere in between 912, which is 927 minus $15, or I might be as high as 942. Less than that, differing by less than $15, includes all the area in between these two boundaries. If I had said instead more than $15, that would take me out to these boundaries, but then I would be concerned about the tail going to the right of that number and to the left of that number. In this case, these two serve as a lower and an upper boundary of my area that I'm targeting. So we put these two numbers, we put the mean of the population, and then we take the standard deviation divided by the square root of 500. And we see that about 90.65% or 0.9065 will differ from 927 by an average of less than $15. Now, this is for a sample of 500. If we were just taking individual families from the population and comparing whether they would fall within $15 of the population mean, we can see that's going to be a much smaller portion of my population. Why? Because 68% will lie within $200 of 927. So 68% would be, using the empirical rule, $200 less. And that would put it at $727. And then to the right, if we went 200, we'd be at $1,127. That's only 68% of my population. But here, I only went to the right and to the left $15, but because we're talking about a family, or 500 families, the deviation is much less. See if you can calculate this. Put it on pause. And calculate the probability. You are correct. The probability, if you correctly price this out, is the value of x. The probability that x bar would fall between these two values is 0.9551. or 95.51%. We can even go in the other direction, and some of the problems on your homework will do so. In this problem, a company produces steel rods. The length of the steel rods is normally distributed with a mean of 150.3 and a standard deviation of 0.7 centimeters, or 7/10 of a centimeter. For shipment, 11 steel rods are bundled together. Find P28. As you guys have worked through your homework, I'm sure you've seen this before. But this is the average length separating the smallest 28% bundles from the largest 72% bundles. P28 means the 28th percentile. So in this case, I'm looking for the boundary value, which I don't know what it is, but the boundary value that would separate the bottom 28% of my data from the top 72% of my data. So in this case, we're being given percent. So we turn to invert norm. In invert norm, the first thing we put is what the area would be to the left of the value we're after. In this case, they told us 28%. So we put 0.28, and we put the mean, and we put the standard deviation. But remember, in this case, the standard deviation is not just 0.7, but 0.7 divided by the square root of my sample size, which is 11. We find it's 150.18. That's the end of this section. I hope you enjoyed it, and good luck on the homework.